In this lab, our goal was to figure out the viscosity of several different fluids, including water, vegetable oil, dish soap, and corn syrup, and relate it to the magnitude of resistive forces a metal ball bearing experiences when in free fall in these various liquids. This is very applicable to real life, as nothing in the natural universe exists in a perfect vacuum. Resistive forces were calculated by dropping an object through various liquids and examining its acceleration at a moment in time, and its viscosities were calculated in turn by solving for mu, which represents viscosity. This will be described in more detail shortly. Our findings indicate that the magnitude of resistive forces in a given liquid are directly proportional to the viscosity of a liquid.
To model our system, we first have a force diagram that shows how the magnitude of resistive forces acting on the ball bearing when it is at its terminal velocity are equal to the force of gravity. If the ball bearing was not yet at terminal velocity, as is the case with 3 of our 4 trials, then the arrow pointing downwards would be longer, representing a net downward force. Second of all, we have a system schema that demonstrates the relevant forces in our experiment and their origins, which are the force of gravity on the ball bearing as a result of the Earth, and the resistive forces as a result of the fluids. Finally, the energy pie charts demonstrate how the gravitational potential energy of the ball bearing decreases relative to its kinetic energy as time passes, and how the total energy of the ball bearing decreases due to it being lost to liquid. In order to conduct our experiment, we dropped a metal ball bearing with a mass of 8.37 grams and a radius of 6.34 millimeters into 50 milliliter graduated cylinders that were filled with a constant volume of 50 milliliters of water, vegetable oil, dish soap, and corn syrup. Videos are recorded of the process, and these videos were then analyzed using the software tracker to determine the acceleration and velocity of the metal ball bearing among all the trials.
In order to calculate the total resistive forces of each of our trials, we chose a point at the bottom of the graduated cylinder and found the difference between the acceleration due to gravity and the net acceleration to find the acceleration caused by the resistive forces. Then we multiplied the acceleration due to resistive forces by the mass of the ball bearing. From there, the total resistive force could be set equal to the drag force plus the viscous force, and all known values could be plugged in to solve for the viscosity, the only unknown value. The net force that acts on an object falling through a fluid is equal to the force of gravity on an object minus the total resistive forces acting upon that object. As time passes and an object falls faster and faster through a fluid, resistive forces increase and eventually become equal to the force of gravity. At this point, the net force is 0, and the object therefore moves at a constant speed downward, a state known as terminal velocity. However, if an object is not moving at a constant velocity, the total resistive forces acting on it can be found by subtracting the acceleration of the object from 9.8 meters per second squared, which is what it would be in a vacuum, and multiplying this value by the mass of the object. This makes use of Newton's second law of motion, which states that a force equals mass times acceleration. Resistive forces in this case include viscous and drag forces due to resistance to changing the fluid flow.
One source of error in our experiment is that we used a coefficient of drag of 0.5 for our metal ball bearing, which assumes that it is a perfect sphere. Additionally, our calculated viscosity for water was quite off, which was likely due to the fact that the video used in Tracker had a significant amount of motion blur, making it difficult to find the same point on the ball bearing from one frame to the next. Finally, human error can account for miscalculations or misread measurements.